I may rejig some couple of items on that schedule for term 2 and slightly refresh it. And still going to leave time, I think, for that classification of groups of low order. It shouldn't be taking up 3 weeks and stuff. So we'll be able to do a bit of rejigging for that. And I want to leave a lot of time for just doing lots of work with the exercises and doing lots of kind of problem workshops. So I think that's really helpful. Okay, so this chapter on homomorphisms, we've been talking about homomorphisms a little bit as we were discussing isomorphisms. So I'll just give a lecture on some of these topics and kind of picking out important points and discussing some of the examples that are there. So when we're talking about homomorphisms, okay, we've already seen the definition really, because we've seen the definition of an isomorphism between 2 groups. And so homomorphisms are more general. So isomorphisms are special types of homomorphisms. And so a homomorphism phi from one group G to another one, H, is a mapping. Satisfying, and we've already seen this condition. The property it has to satisfy is that for every pair of elements from G, phi of the product G1 times G2, which remember is taking place in G, we multiply G1 and G2 together to get another group element of G. But when we take phi of that product, it must be the same as phi of G1 times phi of G2. And that product on the right-hand side, of course, is taking place in H. Okay? So you're multiplying together 2 phi values. Phi values live in H. So you multiply 2 of them together, it's taking place in H. So this is what we referred to before as the homomorphism property. This is exactly the definition of an isomorphism, except for an isomorphism, you have just one word put in there. An isomorphism is a bijective mapping, one-to-one and onto function satisfying this homomorphism property. Whereas a homomorphism property, there's no restriction like that. So the mapping doesn't have to be one-to-one. It doesn't have to. So it can take different elements of the group G and be mapping them all to the same element in H, thereby kind of losing information. Because when you collapse together, effectively collapsing together different elements of G, you're somehow losing, you're losing information about G. Your view of G is becoming a bit blurred because you're grouping things together. But that might be good because that might give you a simplified look at G. Like when we do the factor group, where you clumping together the elements of G, you're losing information about the structure of G, but you're also simplifying it a bit. And also, it doesn't have to be surjective, so we don't have to cover or hit all of the elements of H with the mapping phi. Okay, so we could be taking a homomorphism into a more complicated group. Maybe G is a much larger, richer group than the groups. Maybe H is a larger, richer group than the group G, but we're going to map G into just some subpart of H. So that's the basic definition. So we should look at some examples. And we can take this view. So homomorphisms are mappings between groups that respect the group structure. And if you apply a homomorphism to a group that you're investigating, and you look at the image of it, the image of the group inside the other group H, you're probably getting some kind of a simplified view of H. If the mapping is an isomorphism, then you're getting a group in H which is exactly like the group G, or exactly equivalent to the group G. If you're just looking at a non-isomorphism, homomorphism, then you're probably looking at some kind of simplified version of the group G. So the first example meets this description. So if we consider this phi from the group S3, the symmetric group S3, remember the group of all permutations on 3 symbols, to the group Z2 under addition, remember, this is as a set, is just the set consisting of 0, 1 under addition. And the rule for this is phi of sigma is going to be 0 if sigma is odd, and 0 if sigma is even, and 1 if sigma is odd. Okay, remember, permutations are called even or odd, depending on whether their representations, product of transpositions, contains an even or an odd number of those transpositions. Okay, this is definitely a surjective homomorphism. We do hit everything in Z2 because there is only 2 things. Because there are even permutations, there are odd ones. But of course, it's not injective. You're taking all the even permutations in S3, collapsing them all down up to 0, and all the odd ones, collapsing them all down to 1. So it's definitely losing a lot of information about S3. But what we are retaining here, this is the point Judson makes in his example, what we are retaining here is the information about odd and evens. Odd and even, and how they multiply. I mean, odd and even permutations and how they multiply. Because we can think of under this kind of labeling of 0 as even and 1 as odd, you can view the Cayley table for Z plus as being odd, or even 0 and odd is 1, and the Cayley table for this is when you compose 2 even permutations, you get an even one. When you compose 2 odd permutations, you get an even one. When you compose an even and an odd, you get an odd. Another example, and this is example 11.1 in the group, 11.1 in the book. If G is a cyclic group, oh no, sorry, just let G be any group. So let an element small g be in a group G, then we can define a map from the integers into define a map from the integers to G by mapping any integer n to equal to G raised to that power n. Okay. And this is a homomorphism. You can check the homomorphism property because if you look at what phi of a product, sorry, phi of some, so I'm talking about the integer z. So it's the group of the integers under addition, remember? So if I look at phi of n plus n is the product in the group Z. This by definition of phi is g to the power n plus n. But by the rules of indices for powers of group elements, that's just g to the n times g to the n, which is exactly the image of n multiplied by the image of n inside the group G. And this mapping phi is going onto surjectively onto the cyclic subgroup generated by G. Cyclic subgroup of G, capital G, generated by G. In other words, this cyclic subgroup of G. Of course, So it could be the whole of G if G happens to be a cyclic group generated by that element, little g, then that would be the whole of G. But, otherwise. Any questions about the definition in those two examples? Another example given in the book there, dealing with matrices. This is 11.2. So this is another homomorphism going from GL to R to R star, which is the set of non-zero real numbers. Non-zero real numbers under multiplication. Remember, to form a group, a multiplicative group of real numbers, you have to exclude zero, at least, because zero doesn't have an input. If you just consider all the non-zero real numbers as a group under multiplication, and GL2R is the set of all 2 by 2 matrices with real entries under the operation of matrix multiplication. So this is matrix multiplication, is the operation here. And this phi is defined as we map A to the determinant of A. Of course, the general linear group only consists of invertible matrices. So every matrix in GL2R does have a non-zero determinant. So the mapping is what defined. We're never trying to map a matrix A to its determinant, which is 0, because A is coming from the GL2R. GL2R, remember, is the group of invertible matrices under matrix under matrix multiplication. And the reason this is a homomorphism is because of the multiplicative, what you might call the multiplicative nature of determinants. I.e. that if you take the determinant of a product of 2 groups, that is the same as the product of the determinants. Okay, that's something we know from learning about matrices. Matrix multiplication and determinant interact well. When you take the determinant of a matrix product, it is just the product of the determinants. But really, that statement can be interpreted as that saying that determinant function is a homomorphism. So on the left-hand side here, you've got phi of A times B, whereas on the right-hand side there, you've got phi of A times phi. Okay. This group operation here taking place in GL2R. This group multiplication here taking place in the multiplicative group of real numbers. Okay. So these homomorphisms, are plentiful. Homomorphisms between groups, and some of our well-known properties, that we already understand, like that fact about determinants, that can be interpreted as an example of a homomorphism property of a map satisfying the homomorphism property. Okay. So it's a legitimate thing to study. So the next we have a kind of familiar type of result. Once we introduce some kind of new concept or definition or new device or tool, we quite often have some basic properties of it. Basic kind of properties which are not too hard to prove, which more or less come immediately from the definition, but give you basic facts about it, sometimes alternative ways of thinking about it, and so on. Okay, so that's what we have in proposition 11.4. We've got four facts presented. So this is all about consider any homomorphism. All facts about a basic homomorphism between 2 groups. And there'll be other such property. I mean, the list is by no means exhaustive. In the exercises, we will find other such properties for us to prove. I believe if we look at the basic, if you look at the exercises on homomorphisms there at the end. For instance, we haven't looked at these very set, but for instance, things like question 9, if you've got any homomorphism and the domain group G is abelian, then prove the image of G, phi of G, which is part of H, actually going to be a subgroup of H, prove that that's abelian. If G is cyclic, prove that the image of G under a homomorphism is cyclic. Okay? These kind of properties, they could have been included in proposition 11.4. There are other basic facts that more or less come more or less immediately from the definition. And they aren't hard facts that need a sequence of lemmas built up to prove them. But we've got some of the basic immediate properties in 11.4 and other ones to discover in the exercises. Okay. So what have we got in 11.4? Well, we got the most important fundamental group kind of properties. So if E is the identity in G1, then phi of E is the identity in G2. Remember, we think of a homomorphism as a mapping that respects the group structure. In the definition, it's presented that it respects the group operation. Phi of a product is the product of the phi's. I should say is the identity. Well, then where can we send the identity element in G1? Well, the identity element is such a special element of G1 where it has to be sent to the identity element in G2. And this is going to come as a consequence of the group homomorphism problem. So we can prove this is that if we think about what phi of E might be, but by nature of the identity, phi of E, well, E we can think of as E times E. So by the homomorphism property, this should be equal to phi of E times phi of E. But this is kind of saying that the element phi of E, whatever it is equal to its square. And how can an element equal its square? Because we've got the group cancellation law. So we should be able to pre-multiply both sides by the inverse of phi of E. Phi of E, remember, at the moment, we just know it to be some element of G2. So it's an element of the group G2. So here we got an element of G2 equal to the square of itself. So if we just cancel phi of E, which we do by multiplying both sides by the inverse of phi of E, phi of E inverse times phi of E equals phi of E inverse times phi of E phi of E. Well, phi of E inverse times phi of E cancels out, and we get the E. Should I call it, I think in the book he calls it E prime, yeah. E prime or well, let's put it better. EH is the identity in the element H. And then these two cancel here, just leaving you with 5. Actually, probably a nicer way to do that is put a subscript G everywhere on the other E's, because they're the identity in G. Like, some books take that approach. So EG is the identity. Oh, sorry. Okay. G. Okay, let's fix that by making that a H there. I think I'm going to regret that later on. Changing notation. Sorry. So phi goes from G to H. So, G is the identity of G. The identity must get matched to the identity. Then for any G G, an element of G, where are we going to map? Where are we going to map G inverse? Well, if you want phi to be respecting the group structure in both groups, it's really only one choice. We're going to send phi, we're going to send G inverse to the inverse of phi G. And that comes about prove this by considering what happens when you multiply phi G with phi G inverse. Well, using the group homomorphism property, that's going to be phi of G times G inverse. But that's phi of the identity, but that has to equal the identity. Maybe drop this out, but this identity here is the identity in the group G, the domain. This identity is the group, is the identity in H in the codomain. Yeah, clear on that? So phi of G times phi of G inverse is equal to the identity. So that means these two elements must be inverses of each other. So that implies phi of G inverse is equal to the inverse of phi of G. Also notice, the slightly different meanings of the inverse notation here. This inverse here is talking about an inverse within the domain group G. That's where little G inverse lives. Whereas that inverse here is talking about inverse within the codomain group H. So we've got those two basic properties. The third basic property is a nice one that says if you've got a subgroup of G, here I'll go back to his notation. So if phi G1 to G2 is a homomorphism, and H is subgroup of G1, then phi of H, and it's clear what we mean by phi of H, phi of a subset of G, we basically here mean the set of all phi of little h over every little h within H. This is certainly a subset of G2. Taking a subset in the domain, map it across using phi into the codomain. This again will be a subset, but if the H was actually a subgroup of G1, then this won't just be a boring subset of G2, it will be a subgroup of G2. It is again a subgroup of G2. Well, that's nice. That's another aspect of a homomorphism respecting the group structure. When you apply it to a subgroup on the left, you get another subgroup appearing on the right. Okay. How should we prove that? Well, we just have to prove that that set phi of H is a subgroup of G2, and anytime we require some kind of subgroup type property, it's going to come, the reason it's going to be true in G2 is going to come from the fact that H is a subgroup in G1. So all the necessary subgroup properties that hold on H get mapped across by phi as well. Okay. So by part two, or by part one, E is an element of phi of H. Okay. The identity is certainly in H, in subgroup H in G1, and when you map it across, phi of E is equal to E, the identity in G2. So that's certainly in phi of H. So phi of H contains the identity. And if an element G, an element phi of G is in phi of H, then the inverse of it by part two, which we just proved, the inverse of it is phi of G inverse. This is also an element of phi H, as G inverse is an element of H. Why is G inverse an element of H? Because H is a subgroup. G started off in H because phi of G is in phi of H, then G inverse has to be in H, so that means the inverse of phi of G
also is in 5H.
So H is a subset which contains the identity, contains inverses. The only other thing we have to do is show that it's closed. Closure. If you take two elements within, take two elements within 5H, i.e. what you're saying there is G1 and G2 are both elements of H. You take two elements of H, G1 and G2, then 5G1 and 5G2 are both elements of 5H. When you multiply them together, we want to show that this is an element of 5H2, that 5H is closed under the group operation. Of course, the only thing to do is to apply group homomorphism property. 5G1 times 5G2 is 5G1 times G2. Yeah, it's just the group homomorphism property. But then what are we looking at? We are looking at an element of 5H since the product G1 times G2 is an element of H. So the closure in property for H in G1 is giving us the closure property for 5H within G2. Okay? So the closure property maps across to the closure property. The inverse, the existence of inverses property maps across to the existence of inverses. The presence of the identity property maps across to the presence of identity. So 5H is indeed a subgroup. Is indeed a subgroup. Well, that property is about mapping subgroups across from G1 to G2. And the very same thing holds to pulling subgroups back from G2 back to G1. So as well as mapping subgroups across the gap from G1 to G2, so to speak, by applying phi, we can also pull back. Pull back is a technical term which people use. Pull back subgroups from G2 using phi back to subgroups of G1. So in other words, if does he use H? Yeah, he uses H. So if H is a subgroup of G2. Okay, so this time your subgroup is starting out in codomain. Phi, so the pullback of H, phi inverse of H. And what do we mean by that? Well, what we're not talking about is the inverse map phi. Because remember, there's no condition here that says that phi is bijective. In order for, so it's a little bit of an abuse of notation or a change in notation. We can't assume that the inverse mapping phi inverse exists on an element level, because the original mapping phi does not have to be injective and surjective. But there does exist a well-defined map which works on a subset level. Okay, so phi inverse of H, which is known as, which can be called the pullback of H. This is defined to be the set of all little g's in G1 with the property that phi of G ended up in H. So it's everything that got sent into H. So if you got any mapping between sets, there does exist this pullback map, not on the element level, but on the subset level. So you can pull back a subset of the codomain back to a subset of the domain. What this property is saying, if you start off with a subgroup in the codomain and look at the set that it pulls back to, that set is itself a subgroup. Okay. Which is nice, because then we know subgroups map to subgroups, and subgroups also pull back to subgroups. But property 4 is saying that then phi inverse is also a subgroup of G1. Okay, again, that just comes down to checking group properties.
and whatever group type property, subgroup type property we need for the subset phi inverse of H, it's going to come from the equivalent subgroup property of that H satisfies over in G2. Okay. Clearly, the identity is in H, and phi V equals E. Those are different E's there. The E on the right is in the group G2. The E on the left inside phi V, that's the identity in G1. So this means the identity in G1 is an element of phi inverse H. Okay, because phi V is inside H. So it has the identity. Does it have closure? I could be making use of one of the more compact subgroup theorems, but maybe clearer just to go through all the group axioms. Does it have closure? Yeah, it does have closure, because if I take G1 and G2 are elements of phi inverse of H, then the question is, where lives the product G1 times G2? Well, by the homomorphism property, it's phi of G1 times phi of G2, but that is again an element of H. Okay, because phi of G1 is in H and phi of G2 is in H, because G1 and G2 started off in the pullback of H. So by definition, they each individually get mapped into H. But then the product of them, of the two images, is also in H, because H is a subgroup. So therefore, G1 times G2 must again be in phi inverse of H, because G1 times G2 gets mapped by phi to something that is in H. So that implies G1 times G2 is an element of the pullback of H. So the pullback is closed under the operation G. And then we just need the inverses property. G is an element of phi inverse of H. Then phi of G inverse, by what we've proved already, this is just the inverse of phi of G. Then that again is an element of H, since H is a subgroup. And the element phi of G is in H. Phi of G is in H, so is its inverse. But its inverse is the image of phi of the inverse of G. So therefore, the inverse of G is in the pullback as well, because it maps to something. So the pullback has the identity, it's closed, and it has all the groups, so it is a subgroup. And then there was this last property, last part of 4, which is a moreover. So not only do subgroups pull back to subgroups, but normal subgroups of G2 pull back to normal subgroups of G1. H is normal in G2, then the pullback of H, pullback phi inverse, which we already know is a subgroup of G1, but it's also a normal subgroup in G1. Well, so what we do is we let, if G is an element of the pullback of H, we need to show for any, or for all elements X in G1 that
xg x inverse is again an element of the pullback.
Don't we? The definition of normal subgroup. Well, sorry, we defined it. How did we define normal? We defined normal as being the left cosets equals the right cosets. It's not the original definition. But an equivalent, one of the equivalent forms for being normal was that a subgroup is normal if whenever you conjugate, that the conjugate of the subgroup is equal to the subgroup. Or alternatively, if you take any element from the subgroup and conjugate it, you again live inside the subgroup. Okay, so X here isn't from the pullback phi inverse of H. X is just any element of G1. So this property has to be true for all elements X of G1. So how can we ever tell if this element xg x inverse is in the pullback? Well, the only way to do it is apply phi to it, look at what it gets sent to, and then argue that it has to be in H. Then we'll know it's in the pullback of H. And H is the thing we know is normal. So we kind of need to map across and make use of the normality of H in G2 and in fact pull back that property into G1 to see that the pullback phi inverse of H is normal in G1. Then, so if we apply phi to xg x inverse, using the homomorphism property, and here we're using it on a triple product, this will break up as phi of x times phi of g times phi of x inverse. But using something we've already shown, phi of x inverse is exactly the inverse of phi of x. See how we're making use of all, previous properties all the time. Now, what are we looking at here? Here we're looking at a triple product in the group G2. Moreover, it's a conjugation by the element phi of x. So you're pre-multiplying by phi of x and you're post-multiplying by phi of x inverse, by the inverse of phi of x. And the element that we're conjugating is phi of g, but by definition, g is in the pullback of H, so phi of g is an element of H. So you're taking an element from the normal subgroup H and you're conjugating it with phi of x. So that must again be inside H because H is normal. Okay? So this is an element of H since H is normal. H is normal in G2. Phi of x is just some element of G2. Okay? So indeed, when you apply phi to this triple product here, the conjugate of g by x, you again live in H. So again, this implies that the conjugate of g by x is in phi inverse of H. So it gets mapped into H. And that shows, i.e., pullback phi inverse of H is normal. It's normal in G1. Okay, then, so following that, there are some more examples given. I'm introduced this property of kernels. Now, you talked about kernels when you did the linear algebra last year. Remember, you had a linear transformation, and the kernel of a linear transformation was a subspace of the domain consisting of everything that got mapped to the zero vector in the code. Well, that's talking about zero vector and the operation of in a vector space. You've got the operation of vector addition that satisfies group axioms. That whole thing can be seen as a group theory stuff. And we can make exactly the same definition in groups. So for any homomorphism of groups from G1 to G2, the kernel of phi, which by definition consists of everything in G1
which gets sent to the identity. And remember, non-isomorphism homomorphisms, they won't be, in general, they're not going to be injective. So it won't, I mean, we know phi of E is equal to E, but there may be a lot of other elements that are also sent to E. So this might be an interesting subset of G1. And this is called the kernel of phi. Note that you can also express it, it's the pullback of the set consisting of just the identity. So the kernel is the pullback of the identity, the set containing just the identity. The set containing just the identity is a subgroup of G2, certainly, the trivial subgroup of G2. So straight away we know now that the kernel is a subgroup. But moreover, the set consisting of just the identity is a normal subgroup of G2. Trivially so. To test whether this is a normal subgroup of G2, just look at what happens when you conjugate it by any other element. When you multiply E on the left by an element X of G2, and post-multiply it on the right by an element X inverse, well, the fact that you've got X, E, X inverse. So you just got X, X inverse, you just got the identity again. So again, you're in the same set. So it's a normal subgroup of G2. Not a particularly interesting one. It's normal because it's the trivial subgroup. But what might be interesting is this subgroup over here, the pullback of it in G1. So we now know that the kernel is a subgroup and it's a normal subgroup of G1. Kernel of phi is a normal subgroup of G1. Now, once we know it's a normal subgroup of G1, the material we were studying a week or two ago on factor groups. So we've now got a normal subgroup of G1. So we can now apply that operation of factor group or quotienting out G1. And this is an interesting construction because it brings us to the first isomorphism theorem. So I'll prove the first isomorphism theorem for you on Friday. I think we'll do that on Friday, and then we'll try doing permutation exercises. We can just do a lot of permutation exercises next week. We'll see. So this leads us to the first isomorphism theorem. And this ties together homomorphisms, isomorphisms, and the concepts of factor groups. And this says if phi is, now I'll match to his notation that he's using here, phi goes from, yeah, he chops and changes his notation around a little bit. So he said psi. So psi goes from G to H, that's the Greek letter psi, remember? Greek letter psi. Then, and if we let K equal the kernel of psi, so K will be a normal subgroup in G. Basically, this isomorphism theorem, we'll look at the precise statement of it and all the maps going on in when we prove it on Friday. But basically, it's saying that if you take the group G and you form the factor group where you quotient out by the kernel of the homomorphism psi, you're actually looking at a group that is isomorphic to psi of k. Remember, psi of k is the image, sorry, psi of g. Psi of g. Psi of g is the image of g. It's what you get when you map the group G across inside the group H. So this is a subgroup of H. It may be all of H if the subgroup, if the homomorphism is surjective, but it might not be all of H.
So it's an interesting subgroup of H. Okay, it's the image of the group G. But we can understand it as a group by building, well, you can either look at it directly as a subgroup of the codomain H, but we can also see a version of it and construct it out of G and see it as a simplified version of G. And exactly what simplified view of G it is this one, where we quotient out by the kernel. Remember when we introduced factor groups, when we were talking about factor groups, we talked about them as a simplified way of looking at the group. You're looking at a group and you're clumping together the elements and subsets, which were the cosets. Clumping elements together and regarding all those elements as being equivalent. And just looking at the group built out of the cosets. Well, what we're doing here is which subgroup are we using to build the cosets? We're using the kernel of psi. So psi might be a non-injective homomorphism. It might take a bunch of elements in G and send them all to the identity element. In effect, what psi is trying to do is it's picking out a subgroup of elements in G, the kernel, and it's saying, really, we want to regard all these elements as being trivial because I'm mapping them all to the identity element in H. So this factor group G takes that on board. It forms a new group out of G. It's a simplified view of G, and it's one where we regard all the elements in the kernel, they're all going to be considered to be trivial. They're all going to be considered to be the identity element. And there'll be a bunch of other elements in this factor group, and that's just looking at kind of what the consequence, if we're making a bunch of elements here in the kernel all trivial, what are the other consequences of that? Well, the other consequences of that are kind of encoded in the other cosets of the kernel that there are in G. So this factor group, what this first isomorphism theorem tells us is that this factor group will be isomorphic to the subgroup of H that is the image of G under that homomorphism. So you've got different ways of looking at the image of G. You can either look at it living over here directly as a subgroup of H, or you can view it as this kind of construction out of G, constructing a subgroup out of G, the simplified view of G, which is going to be isomorphic to that. So we'll look at that in more detail on Friday. We'll go through the proof of it. But it's a really nice result that kind of ties all these concepts. Okay. Leave it there.